Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Before we start, where are you in the homework? Did you install on Windows and you started? You start?
I started.
Okay.
But,
You have still problems?
Sorry,
Okay.
because I had another at 3 p.m. That's why confusion.
Okay. Okay.
I barely started.
You barely started. Okay. You should start very soon, Anila. Okay, so the demonstration was, I think, was straightforward.
No, for me, the tour I started one time, then it has stopped. They told me the data node has been shut down.
Okay, so there must be a problem then.
Yeah.
Okay, so try it, and if you still have time, let me know, and maybe I can look with you, but try at your site first. Okay.
Because I'm using the laptop at the university. There is some.
I solved this issue by creating a local account. I told you that last time. You have to create a local account and make it administrator. Okay, I did that on my laptop. So I couldn't run it on my university account for some reason. I don't know why. But I create another account.
Because they are blocking administrator privileges.
Maybe.
Yeah, they are doing that.
Yeah, maybe. To some extent. It is still administrator, but it doesn't seem fully. So I had to create another account, and it was an administrator, but local account. It's not under the domain. Okay. You can check with IT if you don't know how. Any other issues? Okay. What did we study so far? We had an introduction to MapReduce, then we had an introduction to Hadoop, right? That was 2 weeks ago, and then last week, what did we study? Design patterns. Okay, we studied design patterns. We talked about the basic ideas of these design patterns. From this week, you will see them in real applications. So we'll see dealing with actually three different types of data. Unstructured, and mainly text, structured, relational data, and graphs. And you will see these design patterns in practice, how we will use them, inshallah. Okay. So this lecture, we will focus on unstructured data or text. So to do that, I have to give you a very brief introduction to information retrieval. Don't worry if you don't know anything about it. So the main idea of information retrieval is search. We have some documents, and we have some information need. I want to find something within this collection of documents. How can I find it? So that's the basic idea of the search problem in IR. So given collection of documents and given a query, okay, in this case, of course, text query, and we'll issue this query to the search engine or to the IR system and get back some search results. Okay, so that will be only a running example, just an example of application that we will use especially in this lecture. Okay, so, but you don't need really to know deep what is going on in the search box. Mainly, we have two sides. One side that will deal with documents, and the other will deal with the query. So with the documents, we need to represent the documents somehow in a way that will make the search efficient. So we use what we call representation function here. We represent documents in some format, and we'll do the same to the query. But with that document representation, we store it in what we call an index. Now we do the same with the query. Given the query, we use exactly the same representation function that we used with the documents. So now we have document representations and query representations. Now we are in a good position to compare them. Once we get a query, we compare them, and based on this comparison, we will provide the search results. Okay, so that's basically IR in 1 minute or 2 minutes. As I said, there are two sides. One side that is offline, which is the indexing part. So that's done offline, given a collection of documents. And the search part is done, of course, online. Okay, once we get the query from the user, we want to get some documents that are matching this query. Now, if we are talking about MapReduce, where do you think MapReduce will fit in? Here. In the offline side, right? Because we said MapReduce is good for batch processing. Okay? Although there are, of course, as I think I told you earlier, there are some attempts that use MapReduce for the online side, but mainly it is for the offline side. So what we will do next is to focus on indexing. We started to think about indexing before, right? That was the classical example after the word count example, right? We mentioned that the idea of indexing is to convert the collection of documents that we have into a structure where we have for each term the list of documents in which this term appeared. Okay? Now, why we are doing that? Why are we doing that? That will make it very efficient, very easy, once you get a query, to find out where are the documents that you should look at, you should consider at least. Okay, so we should start with the documents that have these terms. We cannot go, of course, sequentially over all the collection of documents when we get a query. We need to have some efficient data structure that we will use to get some documents that might be relevant to the query. Okay. If we think only about Boolean matching, whether this document has the terms that are in the query or not, then we can use what we call incidence matrix. So in the incidence matrix, we have terms as rows and documents as columns, as you see here. Okay? So for example, if we are given this collection of 4 documents, we can have this matrix that indicates that blue appeared only in document number 2, fish appeared in document number 1 and document number 2, ham appeared in document number 4, and so on. Okay? So what is the problem with this representation? Think about big data now. We have very big collection, which means we have very large number of documents. What would be the problem with this representation?
Big matrix.
It would be a very big matrix. Okay, that's one. What's exactly about this matrix? What's the problem with this matrix? Yes, Samuel.
It holds a lot of empty, in this format you can say cells, empty cells.
Yes, why is that?
Because if a particular word doesn't appear in a particular document, that part will be empty.
Yes. So yes. So this matrix will be sparse. Will have so many zeros. Okay. Because if you think of these terms as the all possible terms that appear in, for example, English, so that's millions of terms, right? Now each document has a very small subset of these terms. So that means that for every column here, we have very few ones and mostly are zeros. Okay, so that's not a good, of course, representation. It won't fit in memory, and that's not efficient. So it's better to use what we call, instead of the matrix, we use linked lists. Okay, and in that specific problem, we call them postings list. Okay, so here, instead of having a complete row, we just save the number of the documents in which this term appeared. So blue appeared in document number 2 only, fish appeared in 1 and 2, and so on. That would be much more efficient, right? Because we don't need to keep track of the documents that don't have this term. Okay? Right. Now this will give us only where the terms appeared, but it doesn't tell us anything about the frequency of the appearance of the terms in the documents. Okay, and of course you can think of the frequency as an indication of importance. If a document is talking a lot about research, then probably you will find the word research appear repeating many times in the document. Okay, so just the indication that it appeared only in the document might not be enough to find good documents if you are given a query. So we will need also to keep track of how many times each term appeared in every document. So it won't be only enough to just have the list of document numbers or document IDs. We'll have to have two things. We'll have to have the document ID, which is the pink here, and also the frequency of the term, or how many times the term appeared in that document. We call this term frequency. Okay, just to keep that terminology in mind. Okay, so this is just before we get this representation. We can also have the matrix, but now instead of zeros and ones, we have zeros if the term didn't appear at all, and otherwise we will have the term frequency. We also keep track, for a reason that we will talk about later, we keep track of the number of documents, okay, in which each term appeared. So for example here, cat appeared in one document, so to keep track, we'll have that number explicit, although this is actually the number of documents that appear in the list, but we keep it here for efficiency reasons. We'll talk about it later. Fish appeared in 2 documents, so we have 2 here. So the green ones are the number of documents that had this term. We call this document frequency. Okay? So we said 2 terminology so far. Term frequency, which is the frequency or the number of occurrences of a term in a document, and document frequency, which is the number of documents in which this term appeared, regardless of how many times the term appeared in each of the documents. Okay, is that clear? Okay. Now sometimes also we need to keep track of where exactly the terms appeared in the document. Okay, so 2 terms appearing very close to each other in the document, that might be a very important signal. If these 2 terms appeared in the query, that is of higher strength than 2 terms that appear very far in the same document. So keeping track of the positions is also important in search. So as you see, we can add other information also. So far we had the document number, which is the pink here. The blue ones are the term frequency, and the yellow ones are the positions. Okay, and the number of positions, of course, is the term frequency. Okay. Now, how can we do that using MapReduce? We already discussed that, I think, 2 weeks ago. So the basic idea is to map over what? What should we do in the map here? So we want to get something like this eventually. Given the collection of documents, we want to get this index as an output from the reduce phase. Okay, so what should we do in the map? So we'll map over documents, right? So each map function will take a document, okay, and tokenize it, get the individual words or tokens, and produce the term, the document number with the frequency. Okay, so now the output will be, the key will be the word, and the value will be the document number and the term frequency for that term in that document. Okay, we discussed that before. We do that for every document. Now what will happen in shuffling? All the values that are associated with the same key will be grouped together. Okay, so in the reduce, we get all the values for cat, all the values for fish together. So that will be very handy to just create the posting lists. Okay, each one of these, by the way, we call it a posting. Okay, so each one of these is posting, the whole thing is posting lists. Okay, so that's the basic idea. We'll map over documents, we'll shuffle, we'll reduce when we do reducing. We need to sort the postings, so that's the requirement in IR in that application, that we have to get the posting list sorted by document ID, sorting by some criteria. Usually it is document ID or document number. Okay. Here is the pseudocode. So here we get the frequency of the words. We emit for all the words, the unique words in the document. We emit one posting, which is the document ID, and here is the document ID. Okay, that's input, document ID, and the frequency. So h of t here is the frequency of the term in that document. And then in the reduce, we'll have to get all the postings which are grouped for that key, for that term. So we append one after the other, and then we have to sort at the end. Sorting here serves two purposes. The first one, it is mandatory for efficient search. Okay, you see the online site when we get a query. Okay, it's very important. It's very critical that these lists are sorted by document numbers. And the second one, the sorting will be useful also for compression reasons. So we'll have to sort the list. Okay. Now, how can we do that with positions? I think it's straightforward. Besides emitting the document number and the term frequency, we also add the positions from all, and then we combine them at the end. So that's straightforward addition. Any questions so far? So we kind of went through that before. I think you saw this setup before. Questions? And you have questions, seems. No? Okay. Okay. Right. So where is the problem here? That's the same pseudocode that we saw. Is there any problems with this code, with this setup? Think big. Okay, when we have big collection, will that be okay? Is there any problem with the map side? The map function takes just one document and produce the for each term the term frequency for it. Any problem with that? No problems? How about the reduce? There's no, by the way, there's no problem logically. There's no logical problem here. Okay, so that code logically is correct. Okay. Of course. So that's all what we care about in this course. Efficiency. Yes. But what is exactly? Yes. Amen.
Can the sorting be done before the reducer, like during shuffling?
How? Shuffling doesn't do any. It does do sorting, yes, but with this case, it will just sort by what? With this code?
We want to sort by document ID.
By term. Yes, but because the term is the key here, right? So it will sort by term. All terms that will be directed to one reducer will be sorted by lexically, right? Is that what we want?
Did we say we want to sort by document ID?
Yeah, but we are doing that within the reduce function. So we will not benefit by the sorting that is done through the shuffling now. Okay, but that's okay. Maybe we can, maybe we should, but with that code, it does the sorting within the reduce function. Is that a problem? What is required before sorting? What do we do before sorting here? Yeah, look at these two lines.
We create the posting list, right?
We create the posting list unsorted. Okay, so we just add one posting at a time to the list, and then sort it. Okay, which means that this list has to be where? Where is that list now? Before, in memory. Okay, so that list now is in memory, and it might not fit in memory. Okay, why is that? Because we are talking about a big collection, right? That if the posting list is so long, which indicates a very frequent term, okay, like the, for example, it won't fit in memory. It will be really hard to fit in memory.
So we need to save it in this.
So yes, we have to play tricks here. Okay, one is what you said, that we have to maybe sort on disk. Okay, sorting on disk, of course, is not straightforward. So that's the main problem. In order to do that, we have to keep all of these postings in memory, which is a bottleneck. That will not scale. Okay, that will not scale. Is that clear? Kanan, are you with us today? Seems like you are.
No, this is interesting.
Okay. Any questions? Is that clear, the problem here? Okay, type. So the problem is that reducers must buffer all posting association with key to sort, and we might run out of memory. Type. Here is another try. What if we converted this to this? So instead of having the key to be the term, we'll put the document number, okay, within the key. What will be the effect of this?
You can sort based on the document.
Yes, so now the shuffling automatically will sort this, right? Will sort based on the new key. Okay, now we can control that. We can define the sorting so that it will be primarily on what? On the term, and then on the document number. Okay, now all of these will be sorted. Would that be enough? Will all of these keys go to the same reducer?
No, we have to
Specify.
Yeah, we have to.
specify it in the function.
So which function?
Partition.
Partition. Okay. How many functions we deal with in MapReduce? There are just 4, right?
Combine.
Map, reduce, combine, and partition. No, nothing else. Okay, nothing else. So we'll have to define the partitioning function here to make sure that the to make sure that the partition will depend only on what here. So the partition number will depend only on
the element fish or
on the term. Okay, on the term. Okay, it shouldn't depend on the document number. If that's the case, then all of the records that have the same term will go to the same reducer. And once we define the sorting function to make sure that we sort first on term, then on document ID, which means that all the keys that have the same term will appear after each other, then that will be done. Okay, so the framework will do the sorting here for us. Where have we seen this before? Did we see that before?
Yes, when we were talking about the design patterns.
Yeah, so that was one of the design patterns, right? Do you remember the name? Huh? Who is talking? Sequence? No, that's not stripes. That's not pairs and stripes. Huh? The first one was what? In mapper combining. Is that in mapper combining? No. So that was called order inversion. Okay, that was called order inversion. If you remember, we talked about two things. We talked about the sorting and the partitioning. Okay? And here is one application of it. Okay? Question? No? Okay, now here is the new code with that design pattern. The mapper doesn't change because we don't need the sorting and partitioning is not about what the map function is doing, right? But here the partition function takes the key, okay, and the value. It of course it will ignore completely the value and also will ignore the document number. So will only based on the term, and it's just a hash, a normal hash function. Yes.
Based on this partition function.
Yeah.
It's not possible to sort on value, right?
It's not possible to sort on value.
Yes.
Shuffling, sorting is always on keys. So there's no way, whether with this function or another, to sort on values. But if you want to sort on current values, then you have to move the value, as we mentioned last time. That's another design pattern, to move the value to, which is actually included also here, by the way. Right? We took one of the value, the part of the value, which is the document number, and we moved it to the key, so that the sorting will be based on both. Okay, but the partitioning here, as you see, only depends on the term. Okay. Yes. Yes.
So when it sorts, it will sort based on.
Sorting is not seen here. Yeah, but when we sort, yes, we will sort first on term, and when we have to break the tie, we will use the document number. Okay. Any question about this partitioning function? Then this is the reducer. So the reducer is a bit more complicated than what we had before. So we have the initialization function. Okay. In the initialization function, we will create the posting list. Remember here that we will depend on the fact that we will keep the state over different cores of the map, of the reduce. Okay. So we will initialize a posting list in the beginning. We will use it, and then we create. We will reuse it over time. Okay. So forget about t previous now. We'll just create a new posting list at the beginning, and then when we get a new value, a new key and value pair. First, let me ask you a question. Usually, when we talk about a reduce function, we have a key and a list of values, right? Because that's the output from the shuffling. Shuffling is group by function, right? So we generally it is one key and list of values, right? Right. Is that the case here?
No.
Why not?
Because the key is separate. Like you have the document number in the key, right?
Yes, inside the key we have the document number.
Yes. So each document is given to a separate mapper, which means each output from the mapper will have a different document number.
Okay.
So you will.
No. Just a second. Mapper or reducer? You mean mapper?
Yes.
Each key from the mapper will have different document number. Actually, this is wrong.
If you have the same term, for example, fish, in document.
In different mappers. Then yes.
So the first document will be handled by one mapper. It will have a different document number, and in another document it will be a different document number. So you want combine them during the shuffle.
Very good. Which means that for every key,
You will have one value.
we will have only one value. We'll have only one value. It won't be 0, it won't be more than 1. It will be only 1. Okay? Because we always have, because the term appeared in that document, and it has just one term frequency. So every key here, it won't be a list. It's a list, but of one value. Okay? So actually, there is no grouping happened in shuffling in that case at all. Right? Is that clear? It's only sorting. In that case, it's only sorting because there is no repeated keys at all. Every emitted key from the mappers will be unique. It will not appear in other, it will not be emitted from other mappers. That was not the case when we have just the term, of course. Okay, because the term can appear in multiple documents. But here, the new key is term and document ID, which is unique. It will happen only once. Okay, type. That means that we have just one value here, which we call it F. Type. Now we remember that we sorted based on that key. So the order that this reduce function will get will be something like this. Let's see if we... So it will be something like this. Okay, so we'll have all the records of fish together, and they will be sorted. So we'll get fish 1. That's one call to the reduce function. And then the next will be fish 9 with that value, of course. And then fish 21 with that value. Okay. And then fish 34 with that value, and so on. By the way, what are these values? The positions. Okay, the positions. Don't forget. These are the positions within this document.
Doctor, but in the example, I think we're talking about term frequencies, right?
The term frequency will be here also, but they are yeah. You are right. But both are, these are just example. Yeah, actually, in reality, you will have both. We'll have the term frequency and the positions to be written in the index. But maybe here we can just indicate the positions because the number of positions will be the term frequency. Okay, what I wanted to say is that these keys, the reduce function will be called with that order of keys. Now, remember that we want to create the posting list for each unique term. So all postings for fish will come sorted by document number. Then another term will start, right? So we need here to detect when we have a new term and when we have when that term finish, okay? Or generally when we have a new term, because whenever we have a new term, that means that the previous one has finished, and now we can create the posting list for it. Okay, is that clear? This is exactly what we do here. We check. So the T previous indicates what was the previous term that we saw. Initially, it is nothing. Okay? So if the current T is not equal to the previous one, and the previous one was not empty, that means that we already finished one term, so we should emit the current posting list, because now we should start a new one. Okay? If that was not the case, then we will just append. So that's an intermediate posting now. Okay? So let me show that by example again. I think this will be. Okay, so let's say that this is so let's say that before fish there was anything with E, Egypt. Okay, with all of the document numbers. Then comes fish. Then what is it? E, B, C, E, F, G, girl. Okay, let's assume that these are the keys that are associated to that reducer. Okay, so girl will come with its document numbers. So initially we don't have anything, so we'll keep adding. So the T previous in the beginning is just empty. Okay, so this is a new term, so we'll keep appending to the posting list. So that's what's going on here. If the given T is not like the previous, which is the case initially, and the T previous is not null, so that's not met, so we will just append to the current list. Okay, so we'll keep appending to the current list until we have until we have a new term, okay, which in this case will be fish. So we'll keep adding for Egypt. Once we get fish, now we know that the posting list for Egypt is ready, because we will not get any more keys with Egypt. Okay, is that clear? So once we get a new term, then the previous one is ready to be emitted, which is this line. So we'll emit the complete posting, and we'll just reset it to be ready for the next one. Okay? And notice that we don't return from here. So that's not the end. We'll have to append the new one with the new term. Okay, and we have to indicate that the previous one now is the new term. Okay, so now the new term will be fish. We'll keep getting fish. Okay, so which means that we'll keep appending until we get a new term. Once we get a new term, we'll emit the posting list for fish, and then we keep adding for the new one. For the very last one, we'll have to emit it with the close. Close means we are done with all records. We didn't have a chance yet to emit the last posting list because we didn't get a new one for it. Okay, so we'll have to emit it in the close function. Okay, is this clear? This is very important to understand. Okay, so we'll have to keep track of where we are in the list and emit a new posting list whenever, emit the current posting list whenever we get a new term in the keys. Okay? Any questions about this? Is that clear? Kanaan? Good. Suhaila, Nina. Those guys, I look at their eyes already, so. Okay. Now there is one more thing. I told you that we need to keep track of the document frequency, right? Here is why. We write, so what will happen is that we will write these postings in that order, right? We will keep appending to the posting list in that order. But we need the document frequency for compression. So this list, of course, without compression is very long. We'll have to work to compress it. It's not it's not important for us to know now how the compression is done. That's beyond the scope of the topic here. But let's just keep in mind that we need the document frequency before we get the list. Okay, so we are done with the previous problem now. So this is kind of a new detail that we need to consider. We need to know the document frequency before we write these postings to the posting list. So that's why we say here chicken and egg. Which one is first? We will not be able to get the document frequency here until we get all the postings, right? But we are saying now that we need the document frequency first before we write them. Okay? So we don't know the document frequency until we have seen all the postings, and that should sound familiar to you. Did we see this before also?
I think this was the last event.
The one before the last. Okay, remember when we talked about the running example last time in the second half was the co-occurrence, right, of two terms. And at some point we said that we will need to know to compute relative frequencies. Okay, so here we need to divide by frequency of one of these terms, and we need to know that before getting the co-occurrence frequencies. So that's very similar to that. Okay, do you remember how did we solve it? You will remember in homeworks, it seems. When you do that in homeworks, you will remember. Yes?
We need to add it as the first element, first element that comes to the reducer for the term, for the specific term.
Okay, so you want to say that I want to add this, you want to add here fish, and here the value will be the docking frequency, right? That's what you are saying. Okay. How can we get this?
That has to be done in the Shakti.
Do we have it? Do we have this number? When this data is here, do we have that number? What is that number first? What is document frequency?
Is it the number of documents where this term appears?
Yes. So that's the number of documents that had this term. Type. In the map phase, do we know that? Do we know that number? Can we get that number from the map phase? What do we do in the map phase? We map over the documents, right? Each document is completely independent from the others. So there is no way to know the exact number from the map phase. Okay? But still we need it to be ready before this part. Right? طيب, what can we do? What can we know from the map phase that can help us to get that number?
We can know that this term appeared in this document. So
Yes.
So we can emit the term with, for example, star, as we used last time.
Yes.
With the value 1.
Yes.
And then we make it in the partition function such that all the stars appear first before the other.
It's not the partition function, it's the, what you are talking about is not partitioning now. In the sorting function. Okay, so in the sort, when you define the sort function of the key, remember the writable comparable, which means that you have to define a sort function. So when you define that function, these stars, which will be here within the key then, so we will emit something like this, okay, from the map function, that indicates that this is one document, okay. So but we have to emit just a value here, right? So we'll have to have 1, okay. And if that's the case, then we don't have this. So what we will have instead, from the map function, we will create one record per document, per term in a document. So fish, star, and 1 from each document. Now, if we do that, in the reduce, we will get all the ones, right? So that will be grouped then. Grouping will be useful here, because all the ones will be grouped. Right? And if once we get that special record, what would we do?
You can add them.
We add all of these numbers to get the document frequency. Once we get it, then we can use it in compressing this list. Okay? Clear? So emit in the mapper special key value pairs and make sure that these special pairs come first. This is critical. Okay? It's very critical that this special value comes before all of these numbers. Otherwise, we will not be able to get the DF at the right time. Okay? And of course, we need to do also proper partitioning so that all of these records, that record also will go to the same, but that will be by default, right? With the same partition function that we saw before, it will also direct this to the same reducer. Okay, so here's an example. So the mapper will emit the keys and values as usual, but besides that, it will also emit the star with the ones. So for each term here, it will have a key value pair. Okay, so these are what we call the special key value pairs to keep track of the document frequency. Then in the reducer, we'll get something like this. Can you tell me how we got these? Although in what we wrote ones. What are these?
Frequency in the documents. Number of.
Which document? This, we said that the stars will be emitted with ones here.
Because the key is
Shuffling is not doing any computations, right? So how did we get these numbers? What are these numbers? Can you imagine? Can you think about it?
We can define a combining function.
Yes. And what will the combining function?
The ones.
Yes. So it will group the ones locally.
based on what?
That's the number of documents that.
Because since we are talking about fish.
Yes. Okay, so let's go back here. You understood this, right? Okay. What if I use the combiner That will add some ones together to get, instead of 32 ones, it will just put 32. Okay? Because we don't need, that's a lot, right? These are all different records. That will be huge number of records over shuffling, over the network, to be shuffled over the network. Okay? So these tricks you have to keep in mind when we deal with that big data. That will save you a lot. Okay? So that's out of the combiner now. So that means that one combiner outputted 63 and the other 82 and 27. What do we do? What will we do with these numbers? Now, when we get it in the reduce, what will we do with that? We'll sum them. So the sum of these all will give us the document frequency. It won't be ones now. It will be just now integer numbers. Okay. But the sum of them is the document frequency. Okay. And then once we get the document frequency, we can do the same that we did in the previous pseudocode. And we have seen that before, of course, right? Okay, any question about this? So we saw, I think, multiple things here, multiple patterns actually. We saw order inversion, because now we indicated that there are things that should come first in the sort order. We also saw the key value, the value to key conversion. That was part of the value, and we had to move it. It was here, and we had to move it to the key so that we can use the sorting capabilities of MapReduce. Of course, you can do also in mapper combining. It's not seen here, but it can be done, right? As we saw before.
I don't think we can. Can we? Because each mapper will produce just one.
Okay, let's check. This is the mapper, right? Can we do any in mapper combining? Why not, Aman?
If you're talking about the combining function that we described.
No. Forget about the combining function that we described. Because the combiner function. Because when we talk about in-mapper combining, that's not a combiner function, right? It's something that we will do in the map object. Okay, so that's different. Now think about in-mapper combining. Is there a way to do some computations that will save us? What was the example for which we used in-mapper combining last time, if you remember?
I think we did it for word count.
For word count, okay, and we were combining frequencies, right, of words, okay, from all documents. Here we are talking about one document, right? So can we save something here? Kanan, you are not with us today, it seems.
Why would you say so?
You are very quiet.
I I'm listening.
Okay,
It's not the same as not being there.
you're right. But I expect always more interaction from you. Maybe that was my expectation from the previous lectures.
Is it
It doesn't have, by the way, to work with that exact code. Maybe you can change it. Okay, but is there any ideas that we can do to save us?
Doctor, the associative array that we are using, this is part of the in-mapper combining, right? Rather than emitting each word separately.
It's not, because in mapper combining we use the fact that the state is kept across different calls of the mapper of the map function, which is not used here. This is very local to one document. Okay, so my question is, can we do something over documents? That's the main question, right? And when we talk about in-mapper combining, okay, we need to think of what can we save across different calls of the map function, not within the same map function. خلاص, now we did whatever we can in the map function. I don't think there is more inside one for one record, for one document. Can we do something across documents?
So we can preserve the state and add the terms from different documents.
Add the terms from different documents, or add
the frequency of the
add the postings from different documents, right? Okay, so this document, for example, let's say that we have two documents, document 1 and document 2. Okay, this term x appeared here and x appeared here. Okay, with this frequency and with that frequency here. Okay, we can combine this somehow to say, instead of x with that and x with that, we can have x with two postings. But that will require a change of how we thought about the other parts. Okay, so we leave that. We'll not talk about it now, because that will break the idea of sorting based on the keys. Because now we cannot move the document number to the key, because we have different document numbers here. Okay, but that's kind of in-mapper combining. Okay, is that clear?
This one it will be done after the map finishes the job, because you have one mapper for one document and another mapper for another document.
Let me. I want to be very accurate here, because the word mapper is different from the map call. Mapper is the object, okay, and for one mapper, the map function is called per record, per key value pair. Okay, every call here is one document. So the mapper has multiple, will process multiple documents. Okay, is that clear now? So these come from different documents that are processed by the same mapper. Okay, so this is very similar to the stripes idea. Instead of emitting X, let's say that this is document 1, I will put just the document number here. And this is document 2. Okay, we used to do X and 1 as a record and X and 2 as another record. So this is like pairs, but it's not pairs here, but it's like that. Here it is stripe. So I can actually have a long list of document numbers here. Okay, but of course, as I said, now we cannot do this value to key conversion. We cannot put part of the value here to the key, because now we have more than one document number. It's not just one. Okay, so it will break the rest of the code. So we'll have to think in a different way. But that's a way of doing in-mapper combining. Is this clear? Okay. So you have to keep all of this tools in mind when you try to make your code efficient. And you will have to think of these things, because with big data, when inshallah you try on a big collection, it might take hours easily to process data. So, and maybe days. It will save you a lot if you make this more efficient.